Okay, yeah, I think we'll get started. It's just gone 3 minutes past the hour. So, hi everyone, welcome to the latest in our series of AI Virtual Tech Talks. My name's Tobias. I work on the AI ecosystem team here at ARM. This is one of our bi-weekly series of talks, and it brings you together really with experts from ARM and our partner companies in the AI Partner Program. Each session, we run a different speaker and features a different speaker. We've got the latest trends on development, optimization, best practices, and new technologies in the AI world. So before we get cracking, just to let you know about our upcoming tech talks. So we've got one coming up on November the 3rd and another 2 weeks later on November the 17th. If we can just flick to the next slide, actually, I think they're on there. That'd be brilliant. So we've got more scheduled as well for December, which will be coming soon. We'll be announcing those soon. If you're interested, please do head to the link below and register for them. You would have seen this is the same link you register for this tech talk, so I hope it's not too hard to find. At the end of this talk as well, you'll be asked to fill out a short survey. We'd really love to get your feedback on this talk, and if you've been to previous talks on the whole series. As a little reward for filling it out, it will appear in your web browser after the talk finishes. We'll be entering those external people who respond into a random draw, and you may be selected if you're lucky enough. You may win an Arduino Nano 33 BLE development board. So we're really excited to have everyone here from around the world to hear about this. So I'm going to introduce our speakers in a second, Elsie, Ling Chuang, and Naveen. So they're going to talk today about model deployment and optimization, because when you think about when we're deploying machine learning and neural networks onto mobile IoT devices, we want to make sure there's a whole range of machine learning features, but there's a great deal of resource constraints we've got to take into account. And model optimization is just one of the ways, and really a critical part actually, of how to undertake efficient machine learning. So we're going to hear more about how we optimize and deploy models today. Elsie Ling Chuang is one of our principal software engineers here in the machine learning group. And he's contributed to the machine learning group's IP design via new algorithms for compression and convolution kernels. Before joining ARM, he worked and developed the Snapdragon math libraries at Qualcomm Research and received his PhD in computer science from Drexel University in Philadelphia, with his work on automatic performance tuning and fast algorithms for polynomial arithmetic. We also have Naveen, who's a principal engineer in the machine learning group. Both of Elsie and Naveen are based in San Jose, and he's working, Naveen, on hardware-aware ML optimization. And he contributed to enabling machine learning on the ARM Cortex-M microcontrollers through our SimSysNN libraries. And he's demonstrated multiple ML use cases on microcontrollers as well. He also received his PhD, this time from Arizona State University in 2015, and his current research interests include building energy-efficient ML solutions for IoT Edge. So it's great to have you both here, and I'd like to hand it over to you for the presentation.
Okay, thank you, Tobias, for the introduction, and hello, everyone. Welcome to join us. The initiative of model optimizations was jump-started by Ian Brett, our ARM fellow, to answer the challenges we've seen from enabling machine learning on the edge. As Tobias just mentioned, as we have all seen, the edge devices have very restrictive constraints when it comes to deploying machine learning algorithms. First, they're very limited in terms of size of a memory, small SRAM, and a small flash. They're also very limited when it comes to the computation capability. On the other hand, we're in the middle of a wave that is very exciting, where both software and hardware are introducing features that are specifically tailored to accelerate the machine learning workload. The two diagrams we're showing on this slide represent the two types of MPUs provided by ARM. The left one is Ethos U55 micro MPU, and the one on the right represent our N-series MPUs for the client. The MPUs in general are equipped with special features such as hardware compression that works particularly well when the model is pruned and clustered. The compute elements in those MPUs are typically accelerated to support low or mixed precision. And some MPUs would even have efficient hardware implementation of some most important asymptotically fast algorithms, such as Winograd. And when we move from the training time models to the inference time model, it is also important to fuse the layers into more efficient implementations on the edge. And not to mention the features and the complexities in compiler, in the performance library, and in the driver and the runtime. So we're looking at a lot of constraints, a lot of limited capability, but at the same time, a fast evolving and very diverse set of features. So we would like to share with the audience today that our vision about machine learning solutions is that it needs to welcome this new component for model optimizations, in addition to the existing popular components of software and hardware. More specifically, our vision is about this end-to-end technology exploration. From the left is the starting point of this exploration, where we have the N-optimized machine learning networks that typically take some form of input, may it be vision, voice, or vibration. And at the end of this exploration, we want to produce reliable performance, power, area, and bandwidth numbers for us to co-develop and co-design the features across algorithms, software, and hardware. And here, like I mentioned, this new component for model optimizations, it actually needs to happen before the software and hardware. Here, we are roughly dividing the types of model optimizations into two categories. The first one is something we call architecture optimizations. We're going to touch upon this lightly. And then the second part is what we call deployment optimizations, which will be the focus of today's talk. But before we go to the deployment optimization, onto the architecture optimization, sometimes for arbitrary user-provided model or the models that are designed for different scenarios, such as for training for highest possible accuracy or for inference in the large data center, those models typically have substructures in their architecture that will become performance bottlenecks when deployed onto the edge devices. So we need to actually change those bottlenecks, replace them with something that is more performant for our edge target. And to do that, there are a few typical approaches. One is to have a domain expert. So here the expert not only needs to know the problem domain, such as vision or voice really well, he or she also needs to know the downstream software and hardware, both the features and the limitations really well. And then with some good dose of creativity, they can come up with this handcrafted model that has optimized architecture for the given target. And then one step further from this point is that as experts develop patterns or rules or knowledge to do such architecture optimization, we can distill the knowledge into a rule-based replacement system, which can automate a large portion of the hand manual crafting. And then, of course, here's the neural architecture search, which is promising and also powerful in terms of generating optimized architectures for a given data set and a given target. And I think Naveen will also cover some part of NAS. But now moving on to the actual focus of today's talk, the deployment optimization. Typically, we include techniques such as pruning, quantization, clustering, and algorithms. And we're not just pulling together these techniques into this umbrella term randomly. It is because when we look at the downstream consumers, such as software and hardware, they require us to introduce these properties into the models so we can verify, we can validate those software and hardware features. So looking toward the right side of the exploration flow, for software, we typically have compilers, drivers, and libraries, where we see different levels and different coverage of optimized kernels, very clever way of scheduling work and memory allocation. And when you stack multiple software components together, it's always important to understand the coverage of operators. And then onto the hardware, which could be in the form of models, RTL, or FPGA. Like I previously mentioned, The compression works really well when the models are sparse and clustered, and the Mac engine could run the low precision arithmetic really well, or even sometimes with very specific support for certain asymptotic fast algorithms. So when everything combined, it is critical that at the model optimization stage, the good attributes must be properly introduced into the original models, because otherwise the unoptimized models will not be able to trigger to validate any of the features we have available in the sophisticated software and hardware. Now let's take a closer look at a model deployment optimization. Here is a typical deployment optimization flow. Starting from the left side is the unoptimized models, which typically are trained. And the first step it goes through is something we call algorithmic optimizations, where we may identify some convolutions or other computation nodes and replace it with some more optimized implementations, such as Winograd. And then entering the second phase is what we call the network optimizations, where you perform various types of pruning and also weight clustering. And then the third phase is the deployment optimizations, where we focus on quantization and also have developed a set of very efficient utilities to make quantization as good as possible. And as you can see, this is a process that involves multiple optimizations. So a critical requirement we have identified and actually developed is a collaboration across all the optimizations, meaning that if the pruning happens first, that introduce a good level of sparsity, and then it's followed by quantization, which may involve some level of fine tuning, then the quantization needs to understand there's a sparsity and properly preserve that. Recall that our goal is about end-to-end exploration, which means for the finally fully optimized models, one model should contain all the good attributes needed to validate software and hardware. And another dimension we would like to point out is inclusion or awareness to the hardware. Previously, the model optimization typically optimized to preserve the original accuracies and also utilize some form of proxy numbers for hardware performance. But our recent effort is about bringing in the direct hardware feedback into the optimization loop, such that we'll be able to strike a balance between accurate model and performant models. An overview of the technologies needed for a model deployment optimizations are described on this slide. So at the bottom, we have the utilities that typically would allow you to do some sort of a graph editing and equalization, sensitivity analysis, and performance modeling integration. And then on top of that is sort of the meaty part of the work, where we see the individual optimizations. Although on opening slide, we've talked a lot about the NPU features, so on. But actually, the ARM CPU has been the most popular target for machine learning workload. And in this slide, we also point, certain optimization not only would benefit NPUs, but it would also benefit existing popular ARM IP, such as the CPU, the microcontroller, and the GPUs. And then on top of the individual optimization, there is the layer that ensure the collaborative optimizations as they would preserve the good attributes introduced at the early stage of the deployment flow. And then also experience as we do more and more deep learning in particular, is the importance of the so-called hyperparameters. And not surprising, every individual optimizations in this picture would require its own set of hyperparameters, and how to properly tune the values of their hyperparameters is very critical to the final performance of the optimized models. So here we're just including 3 examples for hyperparameter auto-tuning. The first one is heuristic, which is very deterministic. And then it can also be solved with reinforcement learning. And if you view the tuning as an optimization problem, then the classic optimization algorithm can also be applied to solve the problem. And here the simulated annealing is just one example among many possible options. So we've done all the individual ones and we make sure they collaborate. We also properly tune the hyperparameters to make sure they work really well. What do we get? So here we're looking at a very, very brief summary of optimization results. So on the left is a table that only focuses on the before and after accuracy delta with unstructured pruning. And we can see that for the first 3 image classification models that are all pruned at 50% sparse, they all at least preserve the original sparsity. And as a matter of fact, for ResNet 50 and VGG 16, we see a slight increase of the accuracy compared to the dense baseline. So this really indicate the model at the design time tends to be overly parameterized and has a good level of redundancy. So by pruning and introducing this additional regularization, in some cases will actually make the model slightly more accurate. And then for the other cases, such as MobileNet V1, wave-to-ladder, and DSCNN, they can all be pruned at a level between 50 to even 80% sparse, while seeing only small accuracy degradation. On the right side is 2 radar charts where we show the benefit or reward when we combine everything together, which means these 2 models, and among many, they're fully optimized. They're pruned, they're clustered, and they're quantized. And also, just for the audience information, it may be a little bit confusing, but here for the radar charts along every axis, the smaller the value is, the better the model is optimized, okay? So the purple hexagon on both radar charts represent unoptimized models. So they will have longer inference time, they will have a higher bandwidth, and so on. And the orange irregular polygon shape in both radar charts represent the optimized model's performance. And we can see that in both cases, the error rate stays roughly the same, but by combining multiple optimizations, the optimized models have much better hardware performance, right? We see between 32% to 41% reduction in inference time, and also between 40% to up to 60% of reduction in bandwidth. So this again really shows the significance and importance of having model optimization and as one of the major building blocks of our machine learning solutions. Now let's start to look at individual optimization techniques, and we'll start with pruning. The pruning can be roughly divided into 3 levels in terms of its granularity. The one on the left is what we call magnitude pruning or unstructured pruning, where you select which parameters to prune or to turn to 0 based on the value of their magnitudes. The one in the middle is called a channel pruning, which has a higher granularity level, where we can prune away some channels, effectively shrinking the design of your model. And then the one on the right is something called a structure pruning. So it's sort of like in the middle between the 2 columns to its left, meaning that we can introduce some form of structure into the location or the distribution of your non-zero values. It could be a block structure, it could be a stride structure. And the diagram on the bottom right also shows lately some effort from the industry. In this case, it's a sparsity mask that represents a layer, a toy example that is pruned with so-called a 2-4 fine-grained structure sparsity, meaning that for every 4 element, there are at most 2 non-zero values. And by doing so, there's a very significant implication in terms of the hardware performance. So this really shows a good collection of effort for people who have tried to exploit the sparsity in the ML models. More specifically, the pruning is, like I mentioned, is about inducing sparsity to overly parameterized models. And by doing so, you can improve the model compression and sometimes the computation efficiency. From the structures perspective, the pruning can be thought as unstructured or structured. And in terms of spatial granularity, pruning can happen at per weight, kernel, filter, or layer, and is always going to be a hard balance, act of balance. between compressibility and the actual acceleration. The typical techniques involved in pruning include magnitude-based, variational dropout, and regularization. And of course, we've talked a lot about redundancy and over-parameterization in the models, but if we're not doing pruning carefully, then we can immediately see significant accuracy degradation. So one of the challenges is always about preserving the accuracy. And then the second challenge is always, we can prune the model to be very sparse, but how do we make sure the sparsity translates to better performance? So let's take a closer look at pruning and point out the key concept. The first one is called a pruning schedule. I just mentioned pruning effectively means turning some of the parameters to zero. So you can think of it as undoing the progress you've done with training. So this can be thought as inducing damages to the model. So it's an intuitive idea to avoid doing all your pruning in one shot. Instead, we should increase the sparsity gradually. So we prune and then we leave out some time for the model to recover that kind of a damage. And another important concept is the distribution of the sparsity. When the user mentions, I want this model to be 80% sparse, that really talks about the overall sparsity. But then we have to think, how do we distribute that overall sparsity across all the layers? Given that not all the layers are equal when it comes to impact in accuracy and in latency. So there are a few methods: uniform, heuristic, or reinforcement learning based method, which we're gonna provide some more details on the later slides. And then taking this game one step further, instead of optimizing just for accuracy and some proxy of hardware performance, we can actually directly feed hardware awareness into the optimization process and into the hyperparameter tuning for these optimizations, such as pruning. And then, we could choose to tune for a single optimization, or we can even try to jointly tune for multiple optimizations at the same time. And when these key concepts are properly taken care of, ideally, we want to see the pruning process to look at the diagram on the right. We're on the top, we're tracking top 1 and top 5 accuracy, and you can see that throughout the entire process, there's basically no degradation. But then at the bottom, where we track the sparsity, we can see that that sparsity gradually increased from 0% to 50% in this case. Okay, so some more information about a hyperparameter tuning, especially the first example about the distribution of the overall sparsity. The uniform is the most straightforward and naive approach, meaning that you allocate the same sparsity across all the prunable layers. And in our experiment, this tends to be less optimal. A simple heuristic that is still very deterministic could be computing the per layer target sparsity based on the number of parameters of this layer. So the basic and simple assumption is the more parameters you have, the more redundancy you have for a given layer. So therefore, this layer will be more prunable. So this has demonstrated some good property with preserving the accuracy. And another heuristic-based approach for scheduling your pruning operations is this example where we introduce this polynomial schedule to gradually increase the sparsity. On the right side is something we've seen also from the research community, where people have attempted to use reinforcement learning, where they train an RL agent to take actions for channel pruning configuration and also observe the change of the states and calculate a reward. And by doing this for a period of time, the agent can be trained to learn the best strategy to do such hyperparameter tuning. So these are all the typical methods we've seen, and some of them we have experimented with. Okay, so like I said, we also want to push the boundary further to directly include the hardware awareness into the hyperparameter tuning, which means now we're going to optimize for two objectives. The first one is, of course, the accuracy, and the second one will be some form of hardware metrics. Here it could be latency, compression, bandwidth, and so on. And naturally, we need to evolve our reward function to single objective to multi-objective. So the diagram on the right is a little bit busy, but I want to point out the high level information there. So the three diagrams on the right shows one experiment using simulated annealing that make its decision based on the reward with two objectives, both accuracy and inference per second. The one on the top shows the gradual increase of the reward function as you would expect from a typical optimization process. Then at the same time, we see with the other two diagrams, we also see in this case, both accuracy and inference per second, the two elements that goes into that multi-objective reward function have also increased steadily in this optimization process. So in the end, we have produced a model that is both accurate and fast on device. And the diagram on the left side represents some ongoing effort that is very exciting, where we've joined the search space across multiple optimization, in this case, pruning and quantization. So what it's showing is that by combining and searching a larger search space, there are better parallel frontier compared to doing the optimization individually. So we've done a lot of work by this point to introduce high sparsity, but recall that one of the challenges is once you have the sparsity, how do we translate that to better performance? On the NPU, it is more straightforward because those hardware features will kick in once you have the sparsity, maybe the reduction of the compressed model size or the reduction in terms of the number of max. But here is an interesting example we see from the research community. It shows that even for the unstructured sparsity, it can still benefit the existing ARM IP, such as ARM CPU. So we're not going to talk a lot of details about this, but what this guy shows that by combining the power of pruning and the power of highly optimized sparse mass kernels, you can gain a whole generation of speed up by the power of two on top of existing very competitive models such as MobileNet V1 and V2 and EfficientNet. So it really shows the importance and the power of sparse acceleration across multiple IPs. And along the direction of accelerating on existing IPs, we also have this effort where we have proposed something called a complex domain vinaigrette. And in our early work, it shows more than 2x speed up compared to a highly optimized NCNN library with better SIMD vectorization. And we're pushing the boundary even further by restricting the transform data to just 8 bits, which will give us even better vectorized performance. And at this point, I'm gonna hand it over to Naveen. Please take it away.
Thanks, Elsie.
Yep.
I'll talk about the other model optimization starting from quantization. So neural networks are typically trained in floating point, but such high precision is not necessarily needed for inference. In many applications, it has been shown that int8 or 8-bit integer arithmetic is sufficient to get good accuracy and good performance. So typically, a floating point data can be quantized to int8 using the equation shown here. So by quantizing floating point to int8, we get directly 4x savings in model size and memory bandwidth. And depending on the hardware, for example, in CPUs, depending on the instruction support, we get anywhere from 2 to 4x speed up running quantized arithmetic. So more aggressive quantization, such as like 4 bits or 2 bit, or even going down to 1 bit quantization is an active research area. So now granularity of quantization. So there are many subtle variants in quantization, which has a huge impact on the final quantized model accuracy. So one such example is per channel quantization versus per layer, per channel versus per layer quantization. So as the name suggests, per layer quantization mean we have a single scale and 0 point per layer in the neural networks. Whereas per channel quantization mean you have a scale and a 0 point per channel in each layer. So for efficient neural networks like MobileNet V1 or MobileNet V2, it was shown that per channel quantization is really needed to get good accuracy. If you do per layer quantization, accuracy takes a deep dive. The other dimension to quantization is whether we're quantizing it with symmetric versus asymmetric. So weights which typically have Gaussian-like distribution centered around 0. So they can be quantized with symmetric quantization, whereas activations, especially at the output of ReLU, they don't have any negative values. So if we do quantize them with symmetric quantization, then we are basically losing half of the full range, and will in some compact models that would impact accuracy. The act of quantization involves finding the optimal quantization ranges. So so what I mean by that is it shows on the top right figure that so for example, if we use the very large quantization ranges, so you'll see that you'll get limited resolution, and hence because of that you'll have large quantization error. Whereas the bottom figure, you can see that if we use very narrow quantization ranges, and anything outside the ranges will be saturated to the boundaries. So in that cases, you would still have large quantization error, but due to the saturation error. So the act of quantization involves balancing range, the quantization range, and the resolution. So the typical techniques that are used here are minimizing quantization error or KL divergence. All right. Looks like there is. All right. So here is the typical quantization workflow that is used in the industry. So we start with a pre-trained floating point model and start with quantizing the weights. So this is relatively straightforward because we have the floating point weights with us in the trained model. So using SQNR or K divergence, we find the optimal quantization ranges, and then evaluate the model to make sure that accuracy is preserved. But finding the quantization ranges for activations is not that straightforward because we don't have access to the activations. We have to run the model through some calibration data to capture the histograms or the statistics of the activations. So typically, a few hundreds of calibration data is sufficient to capture the statistics of activations. So from these statistics, we can find the activation quantization ranges. And after that, we can evaluate the model with the weights and activations quantized. So optionally, if training data is available, we can do quantization aware training, or basically fine tuning with quantization nodes or quantization constraints in the graph. So that would further improve accuracy, especially when we are doing aggressive quantization, going down to 4 bits or even down to 2 bits. Quantization basically is realized by inserting quantization nodes, which is a fake quantization node or simulated quantization node at the inputs and outputs of all the operators. So some examples are shown here. So you have a convolution or a concat or residual add, and all the at all the inputs and outputs, a quantization node or a fake quant node is inserted. So what this fake quant node does, in the forward pass, it simulates the quantization, and whereas in the backward pass or in the training phase, what it does is it basically acts as a pass through, or it passes the gradients back as is. It is called a straight through estimator. So this is really needed when we are doing fine tuning during quantization aware training. One important thing to note is that when we decide to run a model in quantized domain, we should quantize all the operators in a model, not just the compute intensive convolutions or fully connected layer. So the other operators such as the residual add or concat, those also need to be quantized. Excuse me. So those also need to be quantized, because after quantization, those non-compute intensive operators could become a bottleneck. The other one to note is that if there is an opportunity to do layer fusion, for example, on the right side we show the convolution, bias, add, batch norm, and ReLU. They could all be fused before doing quantization. So that way we can avoid quantizing the intermediate activations. If we start doing it that way, the accuracy is preserved, as well as the latency is also reduced, because we don't have to run individual operators. We can fuse them together and then run as a single fused operator. Mixed precision quantization. So if the goal of the quantization is to reduce the model size, then why stop at 8 bits? Some layers in neural networks are very or less sensitive to aggressive quantization. So, but how do we find which layer, and how do we find the optimal bit width per layer in a neural network? So that, for example, if we have a layer with, if we have a network with 50 layers, and there are 8 possible combinations in bit width, so that would give us 8 raised to 50 potential solutions to search through. And there are multiple techniques that are used to search for quantization optimal quantization bit width. For example, reinforcement learning and even simulated learning can be used, and there are many heuristics to do that bit width search. So one such solution is shown here. So the sensitivity-based mixed precision quantization. So it's a quick and dirty solution, but gives impressive results. So the simple thing here is we quantize each layer to the lowest possible bit width, and then fix that layer to that lowest possible bit width within some accuracy tolerance, and then go to the next layer and continue the process. But the order in which we choose the layers impacts the total accuracy and also the model size, right? So a solution is to start from sort the layers in the decreasing order of the size or the number of parameters. So we start from the largest layer, so it is compressed the most, and then keep going forward down. So with this method, for MobileNet V2, we were able to get down to 3 bits in some layers, and giving an average bit width of 4.5 bits for the entire model. And before fine tuning, the accuracy drop is 2%, and that out of which 1.5% accuracy is recovered after fine tuning. So for some large layers, such as the final fully connected layers, doing uniform quantization is not sufficient to get good compression as well as maintain accuracy. So in such cases, clustering or non-uniform quantization helps us to achieve better compression. So what do we have to do? How do we get clustering? So the simple thing here that we do is we do k-means clustering algorithm, which is a popular clustering algorithm in traditional machine learning, to find the initial cluster centroids. So once we find the initial cluster centroids, so that is not generally sufficient, because we are doing some approximation, we lose the accuracy because of that. So we'd have to do fine tuning, and during fine tuning, we have to put clustering constraints in the graph. Otherwise, what happens is, let's say you are clustering to 8 clusters and then start doing fine tuning. Again, you'll not get 8 clusters without these clustering constraints in the graph. So we have to make sure that we have clustering constraints in the graph. And typically we do pruning followed by clustering. So when we are doing fine tuning, the sparsity or the pruning, the characteristics of the pruning gets disturbed, or the zeros turned into non-zeros. So we have to insert the sparsity preserving nodes, such as basically which involves multiplying sparsity masks to preserve sparsity when we are doing fine tuning. So here I'll try to graphically explain what the collaborative optimizations mean. So collaborative optimizations mean, what I mean by that is when we do pruning, clustering, and quantization together, and I show how they collaboratively work to improve the model compression. So here I have an example of weights distribution. pre-trained weights distribution in floating point. And let's say we are pruning to 50% or 50% sparsity. And we start doing fine tuning. And then here is how the distribution would look like. There is a big spike at 0, and then a void in close to the left and right of zeros. Here, the weights are still floating point. And then we do clustering. For example, let's do clustering with 8 bits, 8 clusters. Here, we see there are 8 ED clusters here, and still it is a floating point. And then to deploy it on hardware, we'd have to do we have to snap it to int8 grid. So that is this quantization step. So here now the floating point values are converted into int8 values, but still there are only 8 int8 values. So we have to we have to make sure that the sparsity is preserved when we are doing fine tuning for the quantization, as well as the number of clusters, that is 8, is preserved when we're doing fine tuning. So here is the set of operations or the nodes that we do when we are doing fine tuning with the sparsity preservation and the clustering preservation. Basically, we have some initial centroids obtained from k-means, and then we do with the clustering preservation using some the gather operation here, followed by sparsity preservation, which involves multiplying with a sparsity mask, followed by quantization, which I mentioned, the simulated quantization or a fake quant node is inserted. And then during fine tuning, what we get is a distribution like this. So far, I talked about the traditional model optimization, such as the pruning, quantization, and clustering that we do on off-the-shelf models such as a ResNet 50 or MobileNet, right? So we can only do so much if we are constrained by the off-the-shelf models. But if we have an option to train a fresh model for targeted to our specific hardware, then we can do a much better job. So I'll talk about the model architecture optimizations here. So where do we start? We start with efficient neural network building blocks. Let's say the first thing that comes to my mind is the MobileNet V1. So what we do in MobileNet V1 is there is a 3x3 convolution, which is decomposed into efficient 3x3 depthwise convolutions and followed by 1x1 convolution. So this operation saves considerable amount of flops and parameters. So this became popular for popular architecture for CPUs. And then after that, there is the inverted bottleneck with residual connections in MobileNet V2. And till date, this inverted bottleneck block is the best building block for neural networks that is used in all the state-of-the-art models such as MobileNet V3, EfficientNet, and all other models. So basically, what it consists of is a 1x1 convolution, which is called which expands the number of channels, and then followed by a depthwise convolution, followed by a project which compresses the number of dimensions into a smaller number of channels. So that gives a lot of parameters and a lot of capacity to the model, that improving the accuracy of the model within the same flops. The other way to improve the accuracy is to improve the efficiency of the model is operator sparsification. So LC touched upon this, that when we do sparsity, depending on the hardware support, we can try to get improve the performance. So the other option is asymptotically faster operations such as Vinograd convolution or FFT, which would give, depending on the convolution kernel sizes, you would get 2x to 4x speed up. I mentioned about MobileNet V2 being a popular building block, but is it always efficient for all the IP? So here is an example from one of the research papers, especially targeting MobileNet V2 like architecture for edge TPUs. So we show that efficiency is very target specific. For example, here we see the inverted bottleneck consists of one by one convolution followed by 3 by 3 convolution, and then followed by another 1 by 1 convolution. So instead of doing a 1 by 1 and 3 by 3, what happens if you fuse this 1 by 1 into 3 by 3 convolution into a regular 3 by 3 convolution here? So that way you're increasing the number of parameters and the flops. However, if you see that the runtime is only has actually decreased. That is because of the because of the inefficiency of the depth-wise convolutions. Okay. Moving on to the next example. So here is another motivational example where we have 3 by 3 convolution is replaced by a 5 by 5 convolution. So if we replace a 3 by 3 with a 5 by 5, the number of flops increase almost by 2.78x, whereas the runtime is marginally increased only by 35%. So that's a good trade-off, considering that you are increasing the flops by 3x, almost 3x, and you're only increasing the latency very marginally. It is well known fact that like convolutions are the time consuming ones, but we should also take care of, we should also consider the non-convolutional operators. Here is an example where non-convolutional operators are taking a lot of the network time. So this is from Mobile BERT, which is a natural language processing model. And the model consists of some special operators such as layer normalization and Gaussian error linear unit, which is some kind of activation function. So they found that those two layers are taking considerable amount of time on running on CPUs. So simply replaced those the layer normalization with a simple element-wise linear transformation, and GELU with a standard ReLU. That changes the accuracy a little bit. So if you see here, higher is better. So without optimization, the accuracy is 78.5, whereas with this optimization, the accuracy dropped down a little bit. But if you see the latency difference, you get more than 3x difference or 3x speed up with doing this optimization. That gives a lot of room for us to scale up the model to even recover the lost accuracy. Excuse me. Yeah. So that shows us that if we do hardware-aware neural network optimization or a neural network search, we could get a much higher accuracy for the same latency. So considering the diversity in machine learning hardware, for example, we have lots of CPUs, GPUs, and NPUs, right? So they have different programming models, different compute capabilities, or even memory organization. And the same neural network architecture, for example, MobileNet V2 or mobile nets, the typical mobile nets are designed for mobile CPUs. They do not map efficiently on all other IPs. So the neural networks should be aware of the target hardware architecture, and how this is achieved is typically one of the methods is hand tuning the model architectures to fit well to the hardware. Or basically, this is also called rule-based. You have a set of rules, and then you follow one by one, and doing the graph editing to replace the inefficient block with an efficient block. And but that is little time-consuming. Sometimes you cannot get a better. You'll not get global optimal solutions. So for that, the solution is automated neural architecture search have been researched a lot. And in that automated neural architecture search, or NAS, the typical search objectives are to reduce the latency. And the latency proxies that are used in NAS are earlier, it used to be like max. The number of max and number of parameters have been used as a latency proxies, but more recently, hardware performance models, or the actual performance that is measured on hardware, are used in NAS. And the state-of-the-art models searched by NAS today include MobileNet v3 or efficient nets or FBNet or even MobileBut or searched with neural architecture search. I'll just give a brief overview of how the NAS works. I'll not go deeper into this. So NAS consists of a search space, which the search space basically consists of some set of building blocks, convolution or other building blocks, and a search algorithm samples a model, a candidate model from the search space, and then that is trained to get some accuracy. And it is also, the model is also passed through a hardware performance model to capture the latency. And both the accuracy and latency are combined together to get a multi-object to reward function. And from that, the search algorithm finds a better solution based on the current reward. So that way, over a couple of iterations, it will improve the candidate, how it samples the candidate model, and then we get a better accuracy model. So typically, the strategies involve reinforcement learning, gradient-based methods, also called differentiable neural architecture search, or even random search with rejection sampling works even reasonably well. And the performance estimation, typically for some researchers have tried out, instead of fully training a model or running the model through a performance model, they have estimators for the accuracy or latency to make the search much faster at the cost of some error in the estimation. So this figure shows how a high level how the NAS search space looks like. I'll not go deep in detail into this. So the bottom line here is that we should the search space should be large enough to include a lot of solutions, but should be expressive and small enough to be able to search within very short time. So there are different ways to reduce the search space: chain structure, architecture template based, and the cell based. And like I said, the goal is to reduce the search space, but reduce the search space and still be expressive for the NAS to find good solutions. Concluding, so edge device resource constraints and diverse software and hardware features require co-development of algorithm, software, and hardware. Model optimizations bridge the gap between the off-the-shelf neural network models and the existing software and hardware. If you want to get better accuracy model for the same latency, so efficient building blocks and architectures needs to be searched to get higher accuracy and performance. And neural architecture search techniques efficiently navigate the design space to automate the model design. And there are new opportunities in the joint optimization of NAS, pruning, and quantization now. Well, yes. Any questions?
Awesome. Thanks, Naveen. Thanks, LC. We've got quite a few questions coming from folks online, and thanks everyone who's asked questions while people have been talking. I'll start at the top then. We've got a question around just quickly clarifying what you mean exactly by sparsity when talking about pruning and clustering. That's from Hassan.
Go ahead.
All right. So sparsity, by sparsity here, I mean the zeros. So let's say in all this, what I mean by sparsity is we insert zeros to make sure the model is better compressible. Yeah.
Gotcha. Yeah, that sounds cool. And then we've got a couple of questions. Kind of got a three-parter here. Can we use any FPGA board, or does it have to be a specifically made FPGA device?
I don't get the question. LC.
I assume the question, the context, can we use FPGA board for model optimization? Yeah, so FPGA can be one of the possible options to provide hardware feedback into the optimization loop. But realistically, we want to make sure the hardware feedback is provided quickly enough so that this optimization process will not take 2 months. So the time it takes to generate hardware feedback is also important to allow us to perform reasonably large scale search and optimization. So that's my observation, and but I'm not sure if this is exactly what the audience was asking about.
Sure. No, absolutely. Yeah. Do feel free to add any further comment. I think that's apologies for my mispronunciation. If I do mispronounce it, Sanyade. Do feel free if we've missed any points to clarify that further. The next part of his question is, or his her question, apologies, is around if the pruning is dataset related. For instance, some dataset like images may be difficult to prune, or do you just work on tensors in this sense? So is the pruning dataset related, or do you work on the tensor side?
Right. So when it comes to pruning, it's really you can view this problem both as a forward problem, meaning that we require a level of sparsity, either 50%, 60, or even higher, and do our best as we take care of those key concepts I mentioned, and then just report the final accuracy. And then as you change the data sets, the final accuracy would change as well. And because we know some problem domains are just harder to optimize, and also some models that are typically more compact are also harder to prune. And so this is sometimes in practice, it will be like an iterative process. And right now it's probably still active research for a given arbitrary data set. What is the best strategy, or how much sparsity can you expect by restricting yourself to a small accuracy degradation threshold? And then of course, as for the application of sparsity, you can focus on a per tensor level, or you can also do this kind of a global pruning, where when you draw a threshold, that threshold applies to all the parameters across multiple layers. That will result in a different per layer sparsity. And I hope that answers the question.
Awesome. Thank you, Elsie. We've got a couple of minutes just for one or two more. And very quickly from Pramod here, when you prune different layers during the quantization, how does it help with power savings, since the multiplier bit width is the same in hardware? And they wanted to know how also the mixed precision quantization helps during the inference phase.
Yeah, that's a good question. So how does mixed precision help in quantization when in hardware we only run 8, if we run only 8 bits, right? So when we are quantizing down to lower bit widths, so we also, the additional advantage that we get is we are saving the model size, or basically we are reducing the number of parameters. That helps in the bandwidth. That way, if a particular layer is a bandwidth bound or weight bandwidth bound, you are basically speeding up the layer, although you are still running high 8-bit arithmetic.
Gotcha. Awesome. And then final question we've got come in, unless anyone else fires a question in the next minute or so, just because we're running short on time. Clustering usually is uniform or non-uniform is the question. So is it normally uniform or non-uniform? And can you just quickly explain the benefits of clustering, just summarize those? Yeah.
So clustering is always a non-uniform. So basically what clustering uses is that you typically know the distribution. You have a Gaussian-like distribution. So clustering, what it does is it assigns more cluster centroids at the where density is maximum. That way you have less quantization error. So what is the benefit of clustering? So it has the same benefits of quantization. So you would reduce the memory bandwidth, the weight memory bandwidth, by doing aggressive quantization, and especially it helps in the final fully connected layers, where the layers are huge, like millions of parameters. So, and mostly you are bound by the weight bandwidth at that time. So clustering helps reduce the weight bandwidth at that time.
Yeah, brilliant. Okay, so we're just coming up to the hour. So thank you very much for your presentation. It was really, really interesting. I think it's an absolutely critical part, and you've demonstrated how critical it is as a part of machine learning deployment. And thanks to everyone for joining today. Just before we go, just a couple of quick announcements. Obviously, don't forget that in a couple of weeks' time, we've got our next Tech Talk on November 3rd and November 17th. So please do sign up for those. You can find out more about this and about everything we do to do with software developers by tweeting us and following us on Twitter at ARMSoftwareDev. The recording of this presentation will be available by the end of the week on our ARM YouTube channel. And you can also check out our ARM Software Developers YouTube channel, which we launched quite recently. So do check that out. I think there's some really, really interesting content on here, and you'll obviously be able to rewatch this presentation and all the ones before this from the AI Virtual Tech Talk series dating back to June. And then finally, as you finish the presentation, to finish the webinar today, don't forget that the web view will pop up in your web browser. And if you can please fill out the survey and let us know what you thought of today's Tech Talk, we'd really love to hear your thoughts and opinions. And of course, as a little thank you, you'll be entered into a random draw to win an Arduino Nano 33BLE developer board, which should be really exciting. So thanks to Naveen, thanks to Elsie for your awesome presentation today. And yes, look forward to seeing you at our next AI Virtual Tech Talk series.
Thank you.
Thank you.